Hello students, and welcome to another video of a spectroscopic technique. So today we'll be learning something about the NMR spectroscopic technique, which is actually standing for nuclear magnetic resonance. So nuclear magnetic resonance spectroscopy we'll learn about, and in that specifically we'll talk about the chemical shift wherein we'll discuss the position of signals in the spectrum. Now, this technique, that is nuclear magnetic resonance spectroscopy, actually what does it involves? It involves the characteristic absorption of energy by certain spinning nuclei whenever they are kept in the presence of the strong magnetic field. So what happens? Absorption occurs when these nuclei undergo transition from one alignment to the another alignment in the applied field. So let's go into the detail of this technique first. Let's try to understand the basic principle of this technique first. Now, just like the electrons, the nuclei of certain atoms are considered to have spins. Due to the spinning of these charged particles, because we know that nucleus also carries a positive charge, that is a proton within it. So due to the spinning of these charged particles, the circulation of charge occurs, which actually generates a magnetic moment along the axis of the spin, which is being marked over here with a pink arrow. And the black arrow, circle depicts the motion of the charged particle over here. That's it, the nucleus over here. Now actually the generation of the magnetic moment along the axis of the spin actually helps in making these nuclei to act like very tiny bar magnet. When the external field is applied, the alignment of these species is according to the external field applied. And one such nucleus is the proton, the nucleus of ordinary hydrogen. So now if this proton is placed in external magnetic field, then what will happen? Let's see. Now this is my proton, and I have kept this proton in the presence of external magnetic field. As you can see, its own magnetic field has been created, and I have kept it in the presence of external magnetic field, that is B0, having the value B0. Now when I place this proton in the external magnetic field, then its magnetic moment can be aligned in either of the two ways. And what are those either of the two ways? Number one, it can be aligned with the field, with the external magnetic field. And the second position is that it can be arranged, it can arrange itself against the field, that means against the externally applied magnetic field, which is B0 over here depicted by a blue arrow. Now remember that the alignment with the field is more stable, and the energy is required to flip the tiny proton magnet over to the less stable alignment, that is against the field. So what do we want to say over here? Simply it shows that the alignment with the field is actually more stable than the alignment against the field. So since it is more stable, so definitely if it is required to go against the field, to make the alignment against the field, then we need to provide it with some energy. Now the question arises as to how much energy is required to flip that proton. Well, that actually depends upon the strength of the magnetic field applied. That means the greater the magnetic field applied, then definitely you will have to provide more of the energy to that proton, or that proton will require more of the energy to flip to the alignment against the field. given by the expression wherein frequency is proportional to B naught, which is actually the strength of the magnetic field applied in gauze, which is further multiplied by a factor known as nuclear constant or magnetogyric ratio. Now, just like in IR spectroscopy, to measure the amount of energy absorbed, here also we can pass the radiation of steadily changing frequency through the substance, and then we can observe the frequency at which the radiation is absorbed by the molecule. But actually in practice, we do not do it like that. What we do is we vary the strength of the magnetic field. So while changing the strength of the magnetic field, at some position of time, we will arrive at the value, that value of magnetic field, wherein the field strength of the energy that is required to flip the proton actually matches the energy of that particular part of the radiation. Now at this particular instant of time, absorption occurs. Absorption is done by the molecule, and at this point a spectrum is obtained. So this is how we obtain a spectrum in NMR. What do we do? In short, we vary the magnetic field strength, and this is how the spectrum in NMR looks like. Now here comes a twist. You know what? The story of these molecules is actually not so simple as we have discussed up till now, because had it been the situation been so simple so far that we have described, then all the protons in an organic molecule would absorb at exactly the same field strength. And then what will happen? The spectrum would consist of only a single signal that will tell us little about the structure of the molecule. So we won't be able to get the entire information of the molecule. Basically what happens? The frequency at which a proton absorbs, it actually depends on the magnetic field which that proton feels. Means it actually depends upon the effective magnetic field which is felt by that particular proton, and which is not exactly the same as the applied magnetic field. Now the question arises, why does the magnetic field experienced by a particular proton not same as the applied magnetic field? This actually happens because that particular proton that we are trying to study is surrounded by, has other neighbors also. So what happens? The effective field strength at each proton actually depends on the environment of that protons, the neighbors of that protons. Amongst other things, the electron density at the protons and the presence of other nearby protons, which we are referring to as neighbors over here. So each proton, to be more precise, each set of equivalent protons will have a slightly different environment from the other set of protons. So all the protons which have the same environment, we are referring to them as equivalent protons. Whereas the group of protons, or let's say the protons which do not have the same environment, they do not have the same neighbors, they are being referred to as non-equivalent protons. Okay, so each set of equivalent protons will have a slightly different environment from the other set of protons, and therefore will require a slightly different applied field strength to produce the same effective field strength. So from this conversation, we can come to the conclusion that all the protons absorb at different applied field strengths. And it is this applied field strength that is measured. And the result is a spectrum which shows many absorption peaks. These many absorption peaks, they reflect the differences in the environment of different protons, in the environment of non-equivalent protons. And this actually can give almost unbelievably detailed information about the structure of molecule. Let's see how we get it. So here are the aspects of NMR spectrum. wherein we shall look at the different aspects of the spectrum of NMR that we get. So number one is number of signals. What does the number of signals that we get in an NMR spectrum tells us? It simply tells us how many different kinds of protons are there in a molecule. Why? Because all similar protons, all the protons having the similar environment, that means all the equivalent protons will give only one signal. We'll get only one peak-like structure over here. We'll get only single line as a signal for all the protons which have same environment. So that means number of signals, number of those lines in the spectrum, they will tell how many different kinds of protons are present. For example, if we get 4 lines, 4 signals in the NMR spectrum, so that means 4 different kinds of protons are present in the molecule. Okay. Second is the position of signals. The position of signal, what is the value of delta in the signal, in the spectrum? That position tells us about how the electronic environment of each kind of proton is being affected. It tells us about the electronic environment of that particular proton. If let's say for example, near a particular proton we have a carbonyl group and the other molecule wherein no carbonyl group is present in the near to that particular similar proton. So what happens? Due to the presence of the carbonyl group, the shift in the position of the signal will take place. Okay, so this is why we say the position of signal actually tells us about the electronic environment of each kind of proton. Third is intensity of the signals. How intense the signal is. It tells us how many protons of each kind are present. Okay, so if it has high intensity, that means more number of protons as compared to the other signal which does not carry that particular extent of intensity. Number 4 is the splitting of signals. If a signal is splitting further into 2, 3 or 4 or let's say many peaks, then what does that mean? It simply means that the environment of a proton with respect to other is being affected. That means that particular proton has been affected by the presence of other protons on the nearest carbon atoms. So as the number of protons in the nearby carbon atoms increases, the splitting will increase. It follows the n+1 rule. N is the number of protons present in the nearby carbon atom. So what are the points to carry from this short video? Let's have a quick recap. First, we studied about what is NMR, what does it stands for, and what is its basic principle. Okay. Then we studied about the effect of external magnetic field on the proton. What will happen? What are the alignments in which a proton can be aligned actually, and what happens actually when it is flipped to another form. Then we studied about how do we obtain NMR signals. When is a signal obtained? Is it based on the same concept as we did for IR spectroscopy and we learned in IR spectroscopy video, or is it something different? Yes, of course it is a bit different. We are changing the value of the external magnetic field consistently. Okay. Last of all, we came across the information what does an NMR spectrum tells us about the structure of molecule. When we see the spectrum of NMR, what comes to our mind? Seeing the number of signals in that spectrum, seeing the different intensity of the signals in that spectrum. So what are the informations that we can gather from that particular NMR spectrum related to the structure of the molecule? Stay connected with the next video. We'll discuss about the chemical shift with respect to NMR spectroscopy. Take care.